Photo of young girl with a robotic arm. Figure 4.1 Low-level programming languages support little or no abstraction. They allow programmers to write software in languages that are closer to English and are suitable for system software that powers mobile devices with limited energy and computing resources such as prosthetics. Credit modification of Tilly Lockie at the Singularity U, the Netherlands Summit 2016 by Sebastian ter Bergflicker, CC by 20. Chapter outline 4.1 Models of Computation 4. 2 Building C programs 4. 3 Parallel programming models 4. 4 Applications of programming models, the machines we call computers, including modern desktop computers, laptops, and web servers, are remarkably fast and capacious. However, computer hardware is also embedded in devices that do not fit the traditional definition of computers: home appliances, automobiles, smart thermostats, tools, and televisions. Along with being energy efficient and affordable, these devices may also need to be lightweight, portable, or even wearable. For these reasons, embedded systems have meager processing speed and memory capacity. This chapter focuses on low-level programming languages, which are used in practice to create software for resource-constrained devices. Efficiency is critical to making these devices useful and economically viable. The efficiency of embedded software is make or break. In other words, if we can write efficient code that runs fast and uses little memory, we enable technologies that can help people with their daily lives. Therefore, computer scientists place considerable emphasis on the efficiency and speed of low-level languages, which is why low-level languages are important to society. For efficiency reasons, the syntax of low-level programming languages relies on instructions that are computer-centric and challenging for humans to work with. This has led computer scientists to create middle-level languages that emphasize human readability without compromising efficiency. Consider our fictional company, TechWorks, which is bringing a line of next-generation prosthetics to the market. While legacy prosthetics are sometimes awkward to use and limited in function, smart prosthetics can be revolutionary. These prosthetics are computer-controlled, internet-connected, and make use of artificial intelligence, allow those who need prosthetics to enjoy a quality of life that meets or exceeds expectations. Computer control refers to the ability to manage, organize, or run something on a computer, whereas intelligent control is a class of control techniques that use various artificial intelligence computing approaches. For example, artificial intelligence algorithms can accurately determine the intentions of the wearer and control a prosthetic's motion in an accurate and natural way. Internet connectivity means devices can be conveniently controlled by applications, relay telemetry to healthcare providers, and automatically apply over-the-air updates. TechWorks has fitted a small, inexpensive, energy-efficient system-on-chip computer to their devices and are using the middle-level language C to implement these features efficiently. Learning objectives: by the end of this section, you will be able to define low-level programming languages, including assembly language, define middle-level and high-level programming languages, such as C and JavaScript, compare and contrast the various programming paradigms. Algorithms are used to solve computational problems and create computational models. A computational model is a system that defines what an algorithm does and how to run it. Examples of such computational models include physical devices that can run software, programming languages, or a design specification of such. A programming language is a linguistic application of an algorithm, which uses computational models focused on defining notations for writing code. Many computational models have been devised for a host of other applications. There are many different roles and perspectives within the worlds of computer science and software development. The end goal of software development is to create working software that can run on a hardware model, which itself uses a hardware realization of an algorithm that enables specific physical computers to execute software programs. A hardware model is designed for the convenience of a machine, not a human software author, so hardware models are poorly suited to writing code. Computer scientists have created programming languages, which are designed specifically for programmers to develop practical applications. These languages are usually classified into high-level Java, Python, and low-level languages, assembly language. A high-level programming language operates at a high level of abstraction, meaning that low-level details such as the management of memory are automated. In contrast, a low-level programming language operates at a low level of abstraction. Languages like C and C++ can perform both high-level and low-level tasks. Most software is designed, written, and discussed in terms of how a program should work. It is basically a series of steps that provide a direction of how the program must be executed. An example of this would be the MapReduce model, which is used in distributed systems like the Google search engine to produce search results for large data sets using a complex algorithm. Moving even further away from hardware models, computer scientists have also defined an abstract model, which is a technique that derives simpler high-level conceptual models for a computer while exploring the science of what new algorithms can or cannot do. Modern computers are equipped with a central processor, referred to as a central processing unit, CPU, which is a computer chip capable of executing programs. A CPU's hardware model relies on a specific CPU instruction set architecture, ISA, that defines a list of operations that the CPU can execute, such as storing the results of calculations, Figure 4. 2. With the advancements of technology, computer engineers have designed computer architectures with increasing sophistication and power. Examples of hardware models include the MOS Technology 6502 architecture used by the Nintendo Entertainment System, the ARM architecture used by mobile phones, and the x86-64 and AMD 64 architectures used by modern personal computers. Computer engineers design architectures with hardware specifications, such as execution speed or energy use, in mind. Therefore, hardware models are not suitable for humans to use for communicating algorithms. Diagram of CPU model from input to output with black arrows between processor, registers, combinational logic, and main memory, and red arrows between processor functions and CPU, control unit, and main memory. Figure 4.2, a standard CPU model, shows how a program logic applies low-level instructions to an input to get an output. The program leverages registers and memory, black arrows, and the CPU orchestrates the overall execution of the program, red arrows. Attribution, copyright Rice University, OpenStax, under CC by 40 license. A programming model is designed for humans to read and write. A programming model focused on defining a notation for writing code can also be called a programming language. A programming model can be used to implement a software algorithm using a strict set of syntactical rules. A language's syntax can define keywords such as if. The syntax may include a mathematical operator, a fundamental programming operation that combines values, such as plus. The syntax can define punctuation such as. Essentially, the syntax gives the precise meaning for what each of these elements directs a computer to do. The text of a program written in a programming language is called source code. Software engineers have created practically all software by writing source code in various programming languages. Since a programming model cannot directly execute a program, a compiler or interpreter must translate source code from a middle-level or high-level language into something a computer can execute. As mentioned, abstract models are computational models used to think about algorithms in the abstract, rather than being used to create and run software. The goal of an abstract model is to make it easy for people to devise and convey algorithms. Computer scientists use abstract models to create new algorithms, analyze the efficiency of algorithms, and prove facts about what algorithms can and cannot do. An abstract model is not concerned with the details of computer architectures, which makes it easier to focus on these sorts of deep questions. Examples of abstract models include the random access machine, the Turing machine, and the lambda calculus. The random access machine, Figure 4.3, is a CPU that consists of unlimited memory cells that can store any arbitrary value. Just like any other CPU, the PC determines the statement to be executed next. A random access machine can be used to analyze the efficiency of algorithms. A Turing machine, Figure 4.4, is a mathematical model that can implement any algorithm. The lambda calculus is a theoretical computation concept using lambda functions. It was defined by Alonzo Church and inspired the functional programming paradigm, which you will learn more about in programming language paradigms. Diagram of random access machine with level 0, local interconnect, processor 0, 1, 2, 3 to N1, data bus and memory, and how they are all connected. Figure 4. 3. A random access machine has unlimited memory cells that can store any arbitrary value. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license chart with memory at top, arrow down to read head, double arrows with controller, arrow to write head, arrow back to memory. Arrow from external input to controller, then to external output, Figure 4. 4. A neural Turing machine, NTM, leverages the pattern matching capabilities of neural networks in addition to more traditional computational models. It uses a controller that interacts with external memory resources through attention mechanisms that mimic human attention to improve performance. Attribution, copyright Rice University, OpenStax, under CC by 40 license. A function defines how to convert an input into an output, and functional programming is a paradigm in which algorithms are written as mathematical functions. An example of a functional programming paradigm is a recursion. Refer to the following code snippet, where a function is used to call itself. The factorial of an integer can be computed using a recursive function. Import Java. Util, public class recursion, public static int factorial recursion, int val, if val equals 0, return 1, else return val asterisk factorial recursion val 1. Public static void main string args, scanner s equals new scanner system, in system, out println enter an input value, int val equals s, next int, system, out println, the factorial of plus val plus is. Plus factorial recursion val. An algorithm described in an abstract model cannot be run directly. First, a software developer must implement the algorithm, which means translating the abstract algorithm into source code in a programming language. It may be surprising that so many different programming models can exist, and that algorithms can be translated from one model to another. However, this translation is by design. Computer science established the Church-Turing thesis, which is a scientific theory stating that an algorithm can be converted from any reasonable computational model to another. The Church-Turing thesis provides a lens through which computer scientists can invent many computer architectures and programming languages, all of which can run algorithms. Computer scientists have created terminology to make sense of the similarities and differences among all these programming languages. For example, any programming language can be low-level or high-level, or it can fall anywhere on the spectrum. Low-level programming, a programming language's level of abstraction, is the degree to which a computational model, programming language, or piece of software relates to computer hardware. A low-level language has a low level of abstraction, while a high-level language has a high level of abstraction. In a low-level language, the programmer must describe an algorithm in terms that the computer hardware can understand directly. Source code must describe details such as the location of data in memory and the particulars of how the computer calculates arithmetic. Generally, low-level programs execute faster, but are more labor-intensive to create and maintain. In a low-level language, the programmer is forced to think deliberately about how the computer hardware executes, so the finished program usually executes efficiently. However, that deliberate thought takes time and effort. In a high-level language, the programmer is not burdened with thinking about so many details and can finish their work faster while preventing certain types of programming errors from occurring. A compiler automates converting high-level code to low-level code, but that automated process can introduce some inefficiency. In some settings, code performance is more important, and in other settings, programmer productivity is more important, which is why we have both kinds of languages. We can think of low-level programming languages in terms of cooking. When you cook a meal from scratch, you control every ingredient and every detail of preparation, so the finished meal has precisely the taste and nutrition that you desire. An alternative is to prepare a meal that uses some prepared ingredients, and when you do that, you lose a lot of control over details, but the process is significantly faster and easier. There are many examples of low-level programming languages, but the most fundamental language understood by computers is made up of a sequence of digits. Machine code, the sequence of binary digits bits that can be understood and executed directly by a computer, is called machine code, figure 4. 5. Machine code is the most low-level language. It is also known as binary code. It is a program in the native format that can be understood by a CPU in the form of a long series of zeros and ones. Machine code, or binary code, is the only computational model that a computer can execute. A program written in any other language must be compiled or interpreted into machine code before the program can run. The CPU of a computer is a computer chip capable of executing machine code programs, figure 4.6. It is impractical for humans to work with machine code directly because a machine code program is not designed to be human-readable. The patterns of zeros and ones are designed to be convenient for a CPU to decode, not for humans to manipulate, and such programs are long, typically millions or billions of bits long. Another obstacle is that machine code is hardware dependent. As discussed in 5.3 machine-level information representation, every processor architecture has its own machine language, so machine language written for one architecture, for example, Intel x86, cannot work on any other architecture, such as ARM. When the very first digital computers were built, and programming languages had yet to be invented, programmers had no choice but to write machine code by hand. However, this is extremely time-consuming and prone to errors, so is almost never done today. Illustration of machine code with rows of zeros and ones. Figure 4.5 machine code, with its zeros and ones, is the only computational model a computer can execute. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Photo of a motherboard CPU socket. Figure 4.6 A computer chip is a computer's central processing unit, CPU. Credit. Modification of IISI by Reniko/Flickr. CC by 2. Assembly language. The low-level language in which every statement corresponds directly to a machine instruction is called assembly language. Assembly language is a small step above machine code, but is still a very low-level language. Assembly language is a textual representation of machine code. Just like a machine code program, an assembly language program is a series of instructions that a CPU will execute. However, rather than writing the instructions in a binary format of zeros and ones, each instruction has a textual name such as ADD or move. An assembler is a program that translates assembly language source code into machine code. As shown in Figure 4.7, an assembler translates each textual instruction into the corresponding list of 0 and 1 bits. Illustration of assembly language, textual names, passing through an assembler, and translating to machine code, zeros and ones. Figure 4.7 An assembler is a program that translates assembly language source code into machine object code. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. While it is practically impossible for a human to write a complete program in machine code, writing programs in assembly language is viable. Because assembly language is extremely low-level, these programs tend to run quickly, but they are labor-intensive to write and are machine-dependent. This type of programming was sufficient in the 1960s, 1970s, and 1980s when software was written for one-off capital-intensive machines, such as multi-million-dollar mainframes or space vehicles. Programmer labor was comparatively cheap then, and there was no need to move programs to different hardware. But today, we expect applications to be compatible with multiple kinds of platforms, including phone, computer, and gaming systems. Programmer labor is more expensive than computer hardware, so writing entire programs in assembly language is uneconomical. Consequently, programs are often written predominantly in a high-level language, with assembly language used to write short excerpts on an as-needed basis. Writing code in a higher-level language makes it easier to write correct code that does not have defects. Linked to learning assembly language has been used in high-profile, high-budget projects, such as Apollo 11, the NASA spaceflight that first landed humans on the moon. You can examine the assembly code for the embedded computers in the space vehicles, which has been released publicly. Notice how it is quite low-level, perhaps difficult to follow, and reflects an immense amount of fastidious work. Middle-level and high-level programming. As the name implies, a middle-level programming language is at a level of abstraction in between low-level and high-level language and allows for direct hardware access. The C programming language is a middle-level language that has been in wide use since the 1970s. The C++ programming language is a middle-level object-oriented language based on C. In general, the trade-off between low-level and high-level languages is that writing low-level code is laborious and error-prone, but the finished code executes very quickly. High-level code is faster, easier, and safer to write, but does not run quite as quickly. Middle-level code is a compromise that executes nearly as fast as low-level code, yet has some of the productivity benefits of high-level code. Like low-level languages, middle-level languages allow direct access to computer hardware, making it possible to write hardware-specific programs such as operating systems and device drivers. An operating system is the software that provides a platform for applications and manages hardware components. A device driver is a piece of code responsible for connecting to a hardware component, such as a video card or keyboard. Figure 4.8 summarizes the trade-offs between low-level, middle-level, and high-level programming languages. Graph showing high-level language, slower execution, less laborious; low-level, faster execution, more laborious. Middle-level direct hardware control is in between slow and fast execution and less and more laborious. Figure 4.8 as a rule, high-level languages are less laborious to write and slower to execute than low-level languages. High-level languages typically do not support direct hardware control. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Middle-level languages are ideally suited to writing systems software, programs that provide infrastructure and platforms that other programs rely upon. The core part of an operating system that is responsible for managing and interfacing with hardware components is called the kernel. Kernels need direct hardware access, so high-level languages are inadequate. Practically all widespread kernels are written in C and or C++, such as Windows, macOS, Linux, iOS, Android, Xbox, and PlayStation. Compilers for high-level languages, such as Python, Java, and C#, are themselves implemented in middle-level languages, such as C. Figure 4.9 summarizes the various types of programming languages and how middle-level languages overlap with low-level and high-level programming languages. Stack circles from bottom to top: hardware, low-level languages, middle-level language, very high-level language, and high-level language together, human languages. Figure 4. 9 computation models fit onto a spectrum from low to high level. Attribution, copyright Rice University, OpenStax, under CC by 40 license. A high-level language is farther from a hardware model and closer to an abstract model. Source code in a high-level language does not address low-level details and instead focuses on how an algorithm proceeds, such as visit every item in a list. A high-level language is like viewing Earth at a high altitude, revealing large features such as the contours of rivers and highways, whereas a low-level language is like viewing Earth at ground level, which allows for focusing on fine details such as the activity of individual people and animals. Web application frameworks, e.g., React, Node, are written in high-level languages, principally JavaScript. A web framework is a special tool for building and managing web applications. Some common ones used in web clients are HTML5, CSS, and JavaScript. Native Android apps are primarily written in the high-level language Java, and iOS apps are primarily written in the high-level language Swift. Programming language paradigms. So far, we have categorized programming languages according to their level of abstraction into low-level, middle-level, and high-level languages. A different approach is to categorize languages into paradigms. A programming language paradigm is a philosophy and approach for organizing code, the ideas in a program, and the layout of its source code. Real-world programs involve many thousands of lines of source code, which is too much for a human to digest without some kind of organizational structure. Computer scientists have developed several different paradigms for creating this structure. Unlike level of abstraction, paradigms do not fall on a spectrum. Instead, a particular programming language either adheres to the philosophy of a paradigm or it does not. For example, C is a structured procedural language and not an object-oriented language. Without getting into too many details, C is procedural because it allows programmers to place code in functions that can be called from various places in a program. However, C is not object-oriented because C does not allow, like Java does, the creation of objects that are instances of classes. We will broadly explore these different types of paradigms later in this section, but the chapter on Chapter 7 High-Level Programming Languages elaborates on these and other paradigms in more detail. The imperative programming paradigm. In imperative programming, the programmer writes a series of steps that must be followed in order. Source code spells out a precise series of operations that the computer must execute in order. Since the computer is told to take specific actions and execute these statements, the language is referred to as imperative. An imperative is an order or command. Low-level languages are imperative languages, and middle-level languages, such as C, are imperative and include another paradigm. While low-level languages can mimic the style of a structured language, these properties are not inherent in the language itself and must be imposed by the programmer as a practice. Assembly code can easily be written in a non-structured way, declarative and functional programming. Another type of programming, declarative programming, is a paradigm in which code dictates a desired outcome without specifying how that outcome is achieved. Declarative languages are an alternative to imperative languages. In a declarative language, the programmer declares the desired outcome, and it is the compiler's job to create a series of imperative steps that obtains that outcome. For example, the structured query language, SQL, used to query database systems, makes it possible to specify what data should be retrieved from a database, without specifying how the database system should retrieve that data. Functional languages are another alternative to imperative languages. Recall that a function is a mathematical object that defines how to convert an input into an output. For example, given x equals 4, the function letter1d453, letter1d465 equals letter1d465 plus 3 converts the input 4 into the output 7. Functions can be defined in most programming languages and correspond to small sections of code that perform a specific task, such as a calculation. Functions can be defined in most programming languages. Functional programming is a programming paradigm in which algorithms are written as mathematical functions, Figure 410. In functional programming, practically every part of the program is written as a function. The programmer writes functions that convert inputs to outputs, and it is the compiler's job to create imperative steps to evaluate the functions. Diagram showing input x plus 1, arrow to function lambda, f equals lambda x plus 1 print f1, lambda is a function in Python, output is 2, figure 4:10. This diagram shows a functional programming example using Python. Here the function lambda is used to increment the value of x by 1 whenever it is called. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Declarative and functional languages are considered high-level languages because the compiler is creating these steps on behalf of the programmer. Functional languages are discussed in more detail in Chapter 7, High-Level Programming Languages. Structured programming. In low-level languages and early high-level languages such as BASIC, some special statements called conditional statements, using if-then and iteration, called loops, are programmed using an operation called GOTO, a non-structured operation that instructs a computer to jump to an entirely different part of the program. In large programs, these jumps from one spot to another interact in complex ways, so the flow of execution is difficult to understand when attempting to read the code. These sorts of programs are criticized for being messy spaghetti code, Figure 4:11. Structured and unstructured program format of the square root of an integer using sqrt_z, figure 4:11. The same program that prints the square root of an integer using sqrt_z is shown in a structured format and an unstructured format. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Newer languages were developed to help avoid spaghetti code. In a structured programming language, control flow leverages conditionals, e.g. if-then and iteration statements, e.g. while or do-while, and never uses GOTO statements. For example, C is a structured language that includes the conditional statements if and switch and the iteration statements for, while, and do. In proper C, all the code sections that involve conditionals and iteration are written with these statements, and GOTO should not be used. Note that the fact that GOTO is provided as a keyword in the C language relates to the fact that C is a low-level language and programmers at that level are given the choice of using unstructured programming if necessary, although it is not recommended. Link to learning. Read this seminal article about how GOTO statements can be considered harmful, written by Edgar Dijkstra. The benefit of using these statements is that they make the flow of execution clear in the source code. When writing an if, for instance, it is clear which code is inside the if and which is outside. And when mixing an if with a for loop, it is clear whether the if is inside the while or vice versa. These sorts of inside-outside relationships are difficult to perceive in unstructured code. In a conditional statement like if, the compiler executes a line if the condition has been met or is true. Otherwise, it moves to the next statement, import Java, util, public class main, public static void main, string args, scanner s equals new scanner system, in system, out, println, enter an input value. Int val equals s next int cur val equals 10, if val cur val. System, out, println, the value that you entered is greater than the current. Else. System, out, println, the current value is greater than the value that you entered. Inside a loop, like while, the statements are executed only if the condition in the loop is true. Otherwise, the loop execution terminates, and the compiler moves to the statements after the loop. Import Java, util, public class main, public static void main, string args, scanner s equals new scanner system, in system, out, println, enter an input value, int val equals s next int prod equals 1 while val equals 0. Prod equals prod val, val. System, out, println, the factorial is plus prod. There is a substantial upside to making a language structured, and the only significant downside is that it makes the language a bit more high-level. Therefore, among programming languages that are currently in widespread use, all the middle-level and high-level languages are structured. Procedural programming. In a procedural language, each part of the program is a procedure, which is a function in the context of programming. Known as procedural programming, this is a paradigm in which code is organized into procedures, Figure 412. It is a subtype of imperative programming. All procedural languages, then, are imperative, but not all imperative languages are procedural. A programmer designs each procedure to accomplish a specific task and gives it a descriptive name. This allows the programmer to break a large and complicated program into smaller, more manageable pieces, which are easier to write and easier for other programmers to understand. This property of code being divided into small, reusable pieces is called modularity, and it is considered a virtue. List showing code in procedural programming, step-by-step instructions with words, and one in procedural programming in C++, short code. Figure 4.12. This procedural programming comparison relates a real-life scenario, such as making a sandwich, to the corresponding C++ version of the same scenario. In both cases, each step has its own procedure. Attribution, copyright Rice University, OpenStax, under CC by 40 license. For example, in C, a procedure that opens a socket or an internet connection between two computers is called gsocket connect, Figure 4.13. This procedure involves executing a series of imperative commands that use operating system features, such as the transport layer, system calls, and networking hardware, such as network interface cards or NICs, to set up a socket connection. To close that connection and end communication, C uses the gsocket close procedure, which executes a series of commands that shut down the connection. These procedures use the imperative approach to accomplish their respective tasks, so each function contains a series of imperative statements. Diagram showing functions at client end, closed, socket, connect, synsent, established, and at server, closed, socket, bind, listen, accept, listen, synrvcd, established, Figure 4.13. This diagram demonstrates various functions used by the socket on both the client and the server side to establish and close a connection. Credit, modification of TCP Connect by Sebastian Koechlin / Wikimedia Commons, CC by 3.0. A procedural programming language provides syntax for defining procedures, but cannot force individual programmers to follow through with breaking their code up into small procedures and giving the procedures descriptive names. So even when a program is written in a procedural language, the source code may not necessarily be written in a procedural style. Object-oriented programming. Object-oriented code is organized around objects. An object has both data or variables and procedures that work together to represent a specific human concept. For example, in a desktop or mobile application, every button on the screen is an object. Each button has variables to represent information, such as the location and color of the button, and procedures that perform tasks, such as clicking, hiding, or displaying the button. This programming paradigm is known as object-oriented programming. It is a programming paradigm in which code is organized into objects, where each object has both data and procedures. It is a subtype of procedural programming. All object-oriented languages, then, are procedural and by extension imperative, but not all procedural languages are object-oriented. A simple example of an object can be a rectangle used to represent meaningful concepts in real life, such as the rooms in a house or a person or robot and what it can do. Different rooms may have different attributes, representing features that are specific to a kitchen, a living room, or a bedroom. A robot can have a name and age and can receive input commands and respond or print a greeting, as illustrated in Figure 4.14. Diagram of object-oriented programming showing class, objects, attributes, and methods, and procedural programming equivalent showing variables and procedures, Figure 4.14. The object-oriented use of a robot class instantiates robot objects that have attributes of age, name, and greeting and methods of input, output, and print, attribution. Copyright Rice University, OpenStax, under CC by 40 license. Object-oriented programming was invented to help programmers organize their code, and it has been very successful. The most widely used high-level languages, including C++, C#, Java, JavaScript, and Swift, are all object-oriented. Object-oriented programming is discussed further in Chapter 7, High-Level Programming Languages. Learning objectives. By the end of this section, you will be able to Write C code using fundamental elements of the language. Summarize the steps to develop a C program. Understand the process to compile and run a C program. Describe how linking is used in a C program. Understand how to apply version control management. As discussed, a programming language is a kind of computational model that is used to write programs. C is a popular middle-level language that is widely used to create system software. This section is a crash course in the essentials of C. Introduction to C. The C programming language was invented in 1972 by Dennis Ritchie of Bell Labs, Figure 4.15, and popularized by the book The C Programming Language by Brian Kernighan and Dennis Ritchie. C's peculiar name, a single letter, was a pragmatic choice, since C replaced an earlier language named B. C is a procedural, middle-level language that gives programs low-level access to memory. It is a relatively simple language, which makes learning C and creating a C compiler easier than for more complex languages. This combination of features made C an instant hit, and it has maintained great popularity and import to this day. C has influenced other programming languages, too. C++ is a newer language that adds the object-oriented paradigm to C. Photo of Dennis Ritchie. Figure 4.15. Dennis Ritchie of Bell Labs invented the C programming language. Credit: Dennis Ritchie 2011 by Denise Paniagdale / Wikimedia Commons, CC by 2.0. Why is C so popular? Mainly because its designers managed to strike a balance between low-level and middle-level features that allows C code to execute at practically the same speed as assembly language, while allowing programmers to be productive enough to create large, dependable programs. C is the programming language behind much of the lower-level software that we depend on, including operating systems, language compilers, assemblers, text editors, print servers, network drivers, language interpreters, and command-line utilities. Here are some specific software products that are written in C: the Java Virtual Machine, ANSI C; Linux and open source operating system, C, and some assembly; Python C; Mac OS X kernel C; Windows C, C++; the Oracle database C, C++; Cisco routers C; Industry Spotlight; applications of C. C is used in a variety of industries. One example is astrophysics, where scientists write programs that simulate the motion of stellar bodies and control instruments such as telescopes. Owing to the large size of the universe, these simulations involve performing calculations on very large arrays of numbers. C's ability to execute fast and control the layout of large arrays in memory is advantageous for this application. As a relatively simple language, C is approachable to physicists who are not necessarily expert in computer science. Scientific experiments need to be reproducible, which means that code involved in science needs to work even decades in the future. The fact that C has been a stable, popular language for so long means that it is very likely to endure, which cannot be said of newer niche languages. One notable feature of C is the way it handles memory. In a program, we have variables and values. For example, in x equals 10, x is a variable and 10 is the value. Every value in a program is stored in memory. Memory regions are divided into 4 blocks: stack, heap, static, and code blocks. These regions store various parts of a running program. Running programs create and destroy values extremely rapidly, perhaps millions or billions per second, and memory is finite, so memory locations must be reused or else would run out quickly. When a value is created, memory is set aside as allocated memory to hold that value. Eventually, when the value is no longer needed, that memory becomes freed memory, meaning it is given back so that it can be reused. The process of allocating and freeing memory is called memory management. A memory leak happens when some memory is allocated but never freed. A memory leak is a bug that causes a program to waste resources. Severe leaks can waste all the memory on the computer, causing it to become unresponsive or crash. As a middle-level programming language, C requires programmers to handle memory management manually. This type of flexibility must be used with caution, as it may result in creating programs that are not reliable and secure. In high-level languages, memory management is automated. Here are some other notable features of C. Efficient execution. C is lower in expressive power than some other middle-level languages like C++, and yet simple enough that compilers can generate machine code that is comparable in speed to handwritten assembly code. A lot of research and development have focused on creating performance-oriented C compilers. Portability. C can run in multiple computing environments, also known as having the property of portability. Unix was designed to work on various hardware architectures, so the C language is not hardware dependent. The same C code can be compiled and executed on different hardware architectures and operating systems. Modularity, modular programming, refers to the process of dividing computer programs into separate subprograms. A module is a separate software component, such as an error handler, that may be used by a variety of applications and functions within a system. C has language support for modularity. Procedural and structured programming support. C adheres to the procedural and structured paradigms. Data types and operators. Every variable in a C program has a data type. Data types dictate how much memory is used to store the variable, and which kinds of operators can be used with the variable. Recursion support. Recursion is the phenomenon of a system being defined in terms of itself. In code, this means a function may call itself again and again. C supports recursion. However, it does not provide a feature called tail calling that makes recursion efficient, so recursion is not used in C as much as in languages that provide tail calling. A tail call is a function call performed as the final action of a function. If the target function of a tail is the same function, the function is said to be tail recursive, which is a special case of recursion. Tail recursion, also called tail-end recursion, is useful and helps with code optimizations. Pointers. A pointer is a variable that holds the memory address of another variable and points to that variable, figure 416. Pointers play a crucial role in the C language. They are used to store and manage addresses of dynamically allocated blocks in memory in the underlying computer system. Managing hardware devices involves manipulating certain memory locations, and C's support for pointers is one of the reasons that it is used to implement kernels and device drivers. Diagram of a pointer variable. Figure 4:16. A pointer is a variable whose value is another variable's address in memory. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Technology in everyday life. C's application in the early stages of YouTube. C has a variety of integer types, such as short, int, and long. A C programmer needs to decide on the most appropriate type for each piece of information in their program. Smaller types use less memory, but can only store a narrower range of values. On a typical computer, the maximum short value is about 32,000, and the maximum int value is about 2 billion. A good practice is to think critically about how large a particular value might become and pick the smallest data type that accommodates that range. The YouTube programmers faced this issue when they implemented the view counter for YouTube videos. They had to think through, what is the maximum number of views that a video is likely to garner? 2 billion seemed like a safe choice, so they chose int. This decision turned out to be misguided. In 2014, the viral hit music video, Gangnam Style, by the Korean artist Psy accumulated more than 2 billion views, and the view counter broke. The int variable storing the number of views of Gangnam Style overflowed and wrapped around to a negative number. This proved to be an embarrassment for YouTube, who had to quickly change their code to use long instead. What is the most appropriate integer data type, short, int, or long, for the following quantities? The number of people on an airplane. The number of people on Earth. The number of people in a household. The number of dollars in a bank account. High-level languages usually check array indices at runtime, which makes out-of-range bugs easy to identify and fix, but slows down array subscripts slightly. As a middle-level language, C does not check array indices. An array is a storage space where the elements are stored in contiguous memory cells. They are indexed from 0, the first cell, to n-1, last cell. In C, an invalid array subscript will access memory outside of the array variable. If the subscript is only out of range by a little bit, this will access nearby variables, which is a subtle bug that may go unnoticed. A segmentation fault, segfault for short, occurs if the subscript is very far out of range. When this occurs, it will access a memory address that is off-limits to the program, and your operating system will forcibly shut down the program in response. This kind of runtime error can be notoriously difficult to remedy. Out-of-bounds array subscripts are a common source of segmentation fault errors. Every value in a program is stored at a specific memory address. A pointer is a value that contains a memory address. Technically, a pointer should contain the location of a valid data value. However, many memory locations do not contain valid data values, so it is possible to have an invalid pointer that does not hold a valid location. The pointee is the value that a pointer points at. A pointer is analogous to a street address such as 123 Main Street because it refers to a specific location. In that analogy, each building is a pointee. Usually an address is valid and refers to a place you can visit. However, it is possible to have an invalid address that is not a place that can be visited. For example, if the building at that location was demolished. One of the differences between middle-level and high-level languages is that high-level languages either prohibit invalid pointers entirely or provide mechanisms to handle them safely. As a middle-level language, C gives programmers the freedom to create null invalid pointers, which can be helpful when writing code that interfaces with hardware devices. Since all hardware devices do not support the same functionality, the support of individual features by a given device may be indicated as a null/uninitialized pointer, which is fine as long as the program checks for uninitialized pointers to determine if a given functionality is available. However, in general, the freedom of using null-invalid pointers comes with a responsibility to ensure that pointers are always used properly. This has proven to be difficult. Invalid pointers are a common source of bugs in C programs. In C, the programmer is responsible for making sure that character arrays are actually big enough to fit strings, and that strings include the null terminator character. A character array is a string of characters sometimes terminated using a null. An example might be something like char r equals string \0. Overlooking either of these results in bugs. This is a prime example of how middle-level languages, such as C, expect programmers to deal with more details than do high-level languages. Link to learning. The C standard library has dozens of header files and hundreds of functions. It is impractical to memorize all this information. Programmers do not memorize the prototypes, i.e., name and parameters of library functions. Instead, they refer to reference documents and develop the skill of finding information in these documents quickly. These C library reference documents are available in many places. Developing C programs. A programmer spends significant time working in their development environment. Indeed, a professional developer might spend most of their workday using it. It pays to invest some upfront time and attention toward learning your environment and customizing it to your needs so that your ongoing experience will be frictionless and ergonomic. Chefs, mechanics, and other tradespeople focus much attention on cultivating safe and productive workspaces, and in the same way, experienced programmers attend to their development environment. Programmers working with compiled languages, including C, generally work using the cycles shown in Figure 417. Diagram of cycle, problem, algorithm development human, algorithm, program development human, source program, program translation program, executable program, program execution, hardware, program results. Syntax semantic errors return to program development from program translation execution. Figure 417, a typical work cycle, includes multiple compilation steps after a program has been written and is ready for compilation. Attribution, copyright Rice University, OpenStax under CC by 40 license. Specifically, these steps are algorithm development. The developer designs a high-level understanding of what the code will do and how it will do it. They may document the algorithm with pseudocode, a block diagram, or a sketch. In the case of extremely simple programs, the algorithm may be trivial enough that the programmer can keep it in their head. In some cases, a programmer is implementing an algorithm that someone else created and described in a reference work or research paper. Program development. The programmer writes code that implements the steps of the algorithm. Program translation. The programmer runs the compiler on the code. Often, the code has syntax errors, and the compiler provides error messages describing the errors. A syntax error is a violation of the rules for constructing valid statements in the language. For example, the user may have introduced a typo of some sort, like a missing semicolon, or using a keyword as a variable name. In this case, the programmer goes back to step 2, program development, to resolve the errors one by one. Program execution. At this step, the code has no syntax errors, so it's successfully compiled into a runnable program. The developer runs the program and tests that it operates properly. An initial draft of code often has a semantic error, which is when code compiles and runs, but does not behave as it should. When a programmer finds a semantic error, they go back to step 2 to debug the code and fix the semantic error. Eventually, after thorough testing, which requires a specific approach not described here, no more semantic errors can be found, and the code is considered finished. Some C compilers include GCC, an open-source C compiler developed by the GNU project Clang, an open-source C compiler developed by the LLVM project Visual C++, a C and C++ compiler developed by Microsoft, depending on which operating system you are using. There will be many viable alternative C development environments. An operating system is a complex software program that helps the user control the hardware and help with several other applications. Examples include Windows 10 and 11, and Linux versions such as Ubuntu, Fedora, CentOS. You may choose to use an integrated development environment, IDE, which is a program with a graphical user interface that includes a text editor, compiler, and other tools, all in one application. For example, you can install and use Eclipse for C++, an open-source multi-language IDE originally created for Java programming. Eclipse is portable as it is built in Java and can be installed on any operating system. Compiling and running C programs, the compilation process involves several steps. Compiler. High-level language converts to assembler. Assembly converts to machine code linker, a program that performs linking, a process of collecting and combining various pieces of object code into a single program file that can be loaded into memory and executed in practice. Compilers such as GCC bundle all these steps into one command. Usually when you run the GCC command, GCC compiles, assembles, and links a program. To write, compile, and run a simple C program, write text of program, source code using a text editor, and save it as a text file, e.g., my program. C. Run the compiler, assembler, and linker to convert your program from source to an executable or binary. Compilation is necessary for every program to run and perform the desired operation. GCC, wall G, my program, see GCC compiler options. Wall tells the compiler to generate all warnings. These warnings will often identify mistakes. G tells the compiler to generate debugging information. If you don't supply a O option to set an output file name, it will create an executable called A. A C file is called a module. Often programs are composed of multiple C files and libraries that are linked together during the compilation process. If the compiler gives errors and warnings, edit the source file, fix it, and recompile. It is a good practice to work on just one error warning at a time, namely the first one. This is because a syntax error can cause false alarm errors later in the source code, so warnings errors after the first one could be false alarms. We recommend that, when you get compile errors or warnings, you edit to fix just the first one and recompile. Do not try to fix warnings errors after the first one. Consider the following: Hello World C Program 1, include stdio. H** include print prototype **, the simplest C program */ int main int arg, char *** arg, / main program entry point, print hello world \n. Return 0, return without error. To run a program in the current directory on Linux, use program means the current directory. In the world of operating systems, everything is defined in terms of directories and files. Even the desktop is a directory, which is a collection of files. A directory can sometimes be empty too, and some directories have hidden files for security reasons. A subdirectory is a directory within a directory. My program Hello World linking programs Figure 4.18 illustrates the processing steps of C programs from source code to execution. Linking process. Source code, compiler, assembly, assembler, object file, linker input from library, executable, loader input from DLL, main memory. Figure 4.18 The linking process that is used by languages to make them portable requires a number of different steps. Attribution, copyright Rice University, OpenStax, under CC by 4.0 license. Linking refers to the process of collecting and combining various pieces of object code into a single program file that can be loaded into memory and executed. A linker is a program that performs linking. Understanding linkers will help you build large programs, avoid dangerous programming errors, understand how language scoping rules are implemented, understand other important systems concepts, such as virtual memory and paging, and use shared libraries, a file that is to be shared by an executable file. Virtual memory is an operating system concept where the secondary memory acts as main memory to compensate for memory shortage. Paging is a technique where the secondary memory is used to store and retrieve the data into the main memory. The memory is divided into small regions called pages, which enables for the quick access of the data. If a page is found, it is called a page hit. Otherwise, it is a page miss. Programs are translated and linked using a compiler driver. a program that invokes other components that helps in translating the high-level program to machine code, as in Figure 419, and using the following code. Linux GCC OG oprog main, csum, clinux, prog diagram linking source files and separately compiled relocatable object files together to create fully linked executable object file, contains code and data for all functions defined in main. C in sum, C, Figure 419 source files and separately compiled relocatable object files can be linked into an executable object file. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Linkers are used to ensure modularity. Program can be written as a collection of smaller source files rather than one monolithic mass. Using a linker facilitates building libraries of common functions, e.g., math library, standard C library. A library is a file that contains object code, a code from the object file that is generated after compilation for functions and global variables, variables that have global scope and can be used anywhere in the program, that are intended to be reused. Efficiency. It saves time to run separate compilations and change one source file, compile, and then relink since there is no need to recompile other source files. Also, libraries save memory space because common functions can be aggregated into a single file, and yet executable files, the end product after compiling and linking, and running memory images, current memory, contain only code for the functions they actually use. Linking steps programs define and reference symbol. A symbol is an identifier for a function or a global variable. The first linking step performs symbol resolution. During the symbol resolution step, the linker associates each symbol reference with exactly one symbol definition, Figure 420, diagram showing linking, HPP header files, CPP files, C++ programs, O object files, and exe executable files together. Figure 420 in the process of compilation and linking in C++. HPP are the header files. CPP are the actual C++ programs. O are the object files, and exe is the executable. Credit, modification of C++ compilation process by prog/Wikimedia Commons, CC01. 0 symbol definitions are stored in an object file by the assembler called a symbol table. A symbol table is an array of structures in which each entry includes name, size, and location of symbol. The second linking step performs code relocation, Figure 421. This step merges separate code and data sections into single sections, one for code and one for data. It relocates symbols from their relative locations in the O files, the object files, to their final absolute memory locations in the executable. It updates all references to these symbols to reflect their new positions. Diagram showing an array that uses the values of A1, A2, A3 and that includes integers, strings, characters, objects, and aligns with indexes of 0, 1, 2 to N1. Figure 421. This diagram shows the input types in an array and the index locations. Attribution. Copyright Rice University, OpenStax, under CC by 40 license, executable and linkable module format. There are three kinds of object files, modules, that relate to the linking process. Figure 422, relocatable object file, O file. Contains code and data in a form that can be combined with other relocatable object files to form executable object file. Each O file is produced from exactly one source, C file. Executable object file, AOut file, contains code and data in a form that can be copied directly into memory and then executed. Shared object file, SO file. Special type of relocatable object file that can be loaded into memory and linked dynamically at either load time or runtime. These object files are called dynamic link libraries, DLLs on Windows. Hierarchy chart. Executable and linkable module format at top. Arrows down to relocatable object file, executable object file, shard object file. Figure 422. The subcategories of executable and linkable modules are arranged in a hierarchy. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. All three object files follow the executable and linkable format, ELF, which is a standard binary format for object files originally proposed by AT and T-System v Unix, and later adopted by BSD Unix variants and Linux. Unix is an operating system that has been used widely, primarily in servers and software development since the 1970s, and Linux is Unix compatible. Symbol types and resolution. A linker classifies symbols in three categories, as illustrated in Figure 423 and Figure 424. A symbol can be the name of a variable or a string. In other cases, it can be the function names or procedure, such as global symbols, symbols defined by module M that can be referenced by other modules, e.g. non-static C functions and non-static global variables, external symbols, global symbols that are referenced by module M but defined by some other module, local symbols. Symbols that are defined and referenced exclusively by module M, e.g., C functions and global variables defined with the static attribute. Local linker symbols are not local program variables. Linker does not deal with the local variables of a function. Also note that local non-static C variables are stored on the stack, while local static C variables are stored in either BSS or data, code showing linker identifying global and local symbols. Figure 4.23. The code shown illustrates how the linker identifies local and global symbols. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Diagram of relocatable object files and executable object file. Figure 4.24. This diagram illustrates how various symbols are organized in text and data segments within relocatable object files and are mapped into the text and data segment by the linker to create executable object files. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Program symbols are either strong, e.g., procedures and initialized globals, or weak, e.g., uninitialized globals. A strong symbol has a unique memory location. Let's take the example of int array2 equals 1, 2. This creates an ambiguity during the linking process when there is another file that tries to access the same symbol again due to strong definition. On the other hand, a weak symbol allows multiple definitions of the same symbol without creating an ambiguity. This helps during the linking process when another file creates a strong definition of the same name. In languages like C and C++, the weak symbol is defined using the attribute weak keyword. Global variables should be avoided, i.e., use static whenever you can, initialize the global variable, or use extern if you reference an external global variable. The linker applies the following rules. Rule 1. Multiple strong symbols are not allowed. Each item can be defined only once, otherwise the linker issues an error. Rule 2. Given a strong symbol and multiple weak symbols, choose the strong symbol, references to the weak symbol, resolve to the strong symbol. Rule 3. If there are multiple weak symbols, pick an arbitrary one, can override this with GCC FNO common. FNO common helps in catching accidental common name collisions. Static libraries functions commonly used by programmers, e.g. math, I/O, memory management, string manipulation, can be packaged into a file called a library. A static library, or an archive file, is a simple kind of library that copies the contents of object files into a single file called an archive. The linker tries to resolve unresolved external references by looking for the symbols in one or more archives. An external reference is a symbol that is used in a module, but not defined in that module, so it is expected to be defined in some other module. If an archive member file resolves a reference, the linker links it into the executable. The archiver allows incremental updates. It also recompiles functions that changed and replaces the corresponding file in the archive. Figure 4.25. Diagram of ATE, C printf, C random. C going into translator, resulting in ATE, O printf, O random, O then to the archiver R, resulting in libc, a C standard library. Figure 4.25. The diagram illustrates how the R archiver utility is used to create a sample version of the libc. A static library that only includes the ATE, O printf, O and random, O object files. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Commonly used libraries include libc. The C standard library, which handles I/O, memory allocation, signal handling, string handling, data and time, random numbers, and integer math. Another common library is libm. The C math library that handles floating point math, e.g. sin, cos, tan, log, exp, sqrt. Figure 4.26 illustrates how to link programs with static libraries. Diagram creating an executable file using archiver, R, translators, and statics libraries to create linker, LD, a fully linked executable object file. Figure 4.26. This diagram demonstrates the creation of an executable file using various static libraries. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. The linker uses the following algorithm to resolve external references: scan O files and A files in the command line order. During the scan, keep a list of the current unresolved references. As each new O or A file obj is encountered, try to resolve each unresolved reference in the list against the symbols defined in obj. If any entries in the unresolved list at end of scan, then issue error. Therefore, the command line order matters and libraries should be placed at the end of the command line to avoid linker errors as illustrated in Figure 427. Code, Unix GCC, libtist. O lmine/univ GCC, lmine libtist. O/libtist. O in function main/libtist. O text plus 0x4, undefined reference to fun Figure 4. 27. Notice the link errors caused due to the incorrect order of the files. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Concepts and Practice APIs in C. The C language makes it possible to create a modular API, application programming interface, as a library with publicly visible function prototypes, but secret function definitions. This is accomplished by distributing the H files with function declarations freely while keeping the C files secret and instead distributing only, or so compiled object code. H file is used in C, C++, where the libraries can be used in the current program instead of writing the code completely. An example is math. This strategy is used in many industries, such as video games. DirectX is an API created by Microsoft for the platforms that are used on Windows PCs and Xbox. Microsoft provides a C library with many function calls for game-related operations such as drawing graphics, playing sounds, and reading inputs from the keyboard, mouse, or joystick. A game programmer writes their game as a C program that calls those functions. This arrangement is a good compromise. The convenience of the DirectX API makes game programmers work easier and entices them to create games for Windows and Xbox. But keeping the C files proprietary means that Microsoft does not have to give away the hard work that went into creating DirectX, Windows, or Xbox. The same arrangement works on other platforms, too. OpenGL is a cross-platform API that works on almost every modern platform, and Sony PlayStation has a similar API. Both of these are distributed as C libraries with public H files and proprietary implementations. Loading executable object files. An object file is a file that is a combination of metadata from the source or object code, along with a combination of bytecode. Dynamic load time linking. Static libraries have the following disadvantages. Duplication in the stored executables. Every function needs libc, duplication in the running executables, and minor bug fixes of system libraries require each application to explicitly relink. A modern solution to this problem is to use shared libraries, also called dynamic link libraries, DLLs, or SO files. A shared library is a library file that can be shared by multiple programs at the same time, Figure 4. 28. Diagram showing a shared library being used, Figure 4. 28. A shared library can be used by multiple programs simultaneously. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. When using shared libraries, object files that contain code and data may be loaded and linked into an application dynamically at load time, as illustrated in Figure 4. 29. This load time linking occurs when dynamic linking happens at the same time that a program executable is first run. This is a common case for Linux, which is handled automatically by the dynamic linker, LD Linux. So, the standard C library, libc, is usually dynamically linked. The LDD tool may be used to identify dependencies libraries needed at load time. In static linking, the routines code becomes a part of the executable. In dynamic linking, the routines can be updated during the code execution. To dynamically link a library at load time on Linux, place it in the libx8664 Linux new directory and compile the source files with the L flag, gcc main, c lcso, diagram showing object files being loaded and linked, Figure 4. 29. The diagram illustrates how object files may be loaded and linked into an application dynamically at load time. In that case, dynamic linking can occur when the program executable is first loaded and run, i.e., load time linking, which is a common case for Linux that is handled automatically by the dynamic linker, LD Linux. So, attribution, Copyright Rice University, OpenStax, under CC by 40 license. Dynamic runtime linking, an alternative to load time linking, is runtime linking, which means that linking occurs after a program has already started running. As illustrated in the sample code, the program's source code needs to explicitly call functions to link additional libraries. In Linux, this is done by calls to the dlopen interface and compiling the source with the L flag, e.g. gcc main, cldl. This is a better approach to help distribute software, support high-performance web servers, or perform runtime library interpositioning. Hash include stdio, h include stdlib, h include dlfcn, h int x2 equals 1 2, int y2 equals 3 4, int z2, int main, void asterisk handle, void advec, int asterisk, int. Char asterisk error, slash dynamically load the shared library that contains advec, slash handle equals dlopen, slash libvector, so rtl dlazy. If handle fprint fstdir, %s backslash n dlarer, exit 1, get a pointer to the advec, function we just loaded asterisk slash advec equals dlsim, handle, advec. If error equals dlarer, equals null, fprint fstdir, %s backslash n, error, exit 1, now we can call advec, just like any other function asterisk slash advec x, y, z2. Print z equals %d backslash n, z0, z1. Unload the shared library asterisk slash if dl close, handle 0, fprint fstdir, %s backslash n, dlarer. Exit 1, return 0. Tools to manipulate object files. An object file contains a lot of information such as metadata, machine code, and other information from symbols. To manipulate such files, Unix provides certain tools to use them effectively, such as r, creates static libraries and inserts, deletes, lists, and extracts members. Strings, lists all the printable strings contained in an object file. Strip, deletes symbol information from an object file. nm, lists the symbols defined in the symbol table on an object file. Size, lists the names and sizes of the sections in an object file. Readelf, displays the complete structure of an object file, including all of the information encoded in the ELF header, subsumes the functionality of size and nm. Objdump displays all of the information in an object file, useful for disassembling binary instructions in the text section. LDD Linux lists the shared libraries that an executable needs at runtime. Version control management, the process and tools used to store and improve multiple versions of project files, is called version control. Version control also helps support team collaboration and allows for the ability to revert to an earlier versions. Git is a widely used version control system. Creating and updating project files using Git requires the creation of a Git repository, also known as repo for short. A repository is a container for files and related information stored in a version control tool. GitHub is a website that allows free storage of public Git repositories. Link to learn more by installing Git on your local machine on any platform. You may run brew install Git on macOS to install Git or sudo apt install Git on Linux. Useful Git commands are as follows. Git config global user, email you at example.com and git config global user. Name your name clone to download contents pull, git pull origin master to pull latest changes status. Git status to see staged, shown in green, and unstaged, shown in red files staging. Git add file name to add files to staged area, wildcards accepted, commit. Git commit your message here to commit the staged files push. Git push origin master to push all changes made locally to the origin link. To learning, explore the Git GitHub tutorial for more details on how to use Git. Learning objectives. By the end of this section, you will be able to define parallel computing and related terminology. Discuss parallel programming approaches. So far, our programs have run on a single at a time, and the assumption is that the underlying machine only supported a single GPU core. A CPU core is a chip consisting of billions of transistors that function according to an instruction or opcode. It is like a single processor. While there is a lot that we can do with these single-core programs, there is also a need for programs to run in parallel, meaning that they execute code on multiple CPUs, cores, or computers at the same time. In parallel programming, bigger tasks are split into smaller ones, and they are processed in parallel, sharing the same memory. Parallel programming is trending toward being increasingly needed and widespread as time goes on. Many computers now come equipped with a graphics processing unit, GPU, which is a massively parallel processor that supplements a CPU. GPUs were originally designed for rendering real-time graphics in video games and are sometimes called video cards. A typical GPU has thousands of cores, although each is weaker than a CPU core. Parallel techniques are essential for making use of GPUs. Parallel computing overview. In the 20th century, a computer typically had only one processor. Now, a CPU chip typically holds not just one processor, but multiple processors built into a single computer chip. Each individual processor built into a CPU is a core. A multi-core processor is a CPU chip that has multiple cores. Multi-core CPUs are prevalent. Smartphones and budget PCs typically have 2 to 4 cores, and high-end PCs have 8 or more cores. The trend is for these core counts to increase over time. By default, a program runs on one core at a time. That means that a 4-core computer can run up to 4 programs at full speed at the same time. That capability is occasionally useful, but more often a user wants a single high-demand program to make full use of their computer. This is the case with productivity software, games, embedded systems, and web server software. For this to work, the program needs to be coded in a way that explicitly divides work among multiple cores. Fundamentally, in order to use multiple cores, a program needs to work in parallel. That means that multiple cores are working together at the same time, figure 430. A real-world example of parallel work is a factory assembly line. If an assembly line has 20 workers, then at any given moment, 20 people are working in parallel. This concept of parallel work also applies to software. The parallelism concepts discussed here are parallel computer, a multiple processor system that supports parallel programming, parallel computing. The practice of making productive use of parallel computers, parallel programming, a computer programming technique that provides for executing code in parallel on multiple processors. Diagram displaying parallel computing and serial computing. Figure 430, this diagram illustrates how multiple computer programs can be executed as tasks on a multi-core machine, either in parallel on separate individual cores, using parallel computing, or in sequence, on a single or on multiple cores, using serial computing. Attribution, copyright Rice University, OpenStax, under CC by 40 license. There are two related but distinct terms that we should define at this point. Concurrent programming, which refers to any situation where multiple programs or tasks are running simultaneously, regardless of whether they are using multiple processors or sharing one processor. And distributed computing, which is a more specific form of parallel programming where processors are working together in parallel, but the processors are in multiple connected computers, not a single computer. Concurrent programming is a broader term than parallel programming, while distributed computing usually refers to massively parallel programs that run on hundreds or thousands of servers, usually at large companies such as Amazon, Google, the NSA, and the NIH. Then get through GPU applications. GPUs are high-performance parallel processors. Some major applications of GPUs include cryptocurrency mining, video games, and the dashboard computers embedded in automobiles. In 2021, there was a shortage of GPUs due to a perfect storm of world events. The COVID-19 pandemic complicated manufacturing, limiting the rate at which GPUs could be built. In response to the pandemic, demand for computers increased as many workers were forced to work from home. Demand for video games also increased as people sought indoor entertainment. At the same time, cryptocurrency prices went up, which stimulated interest in mining cryptocurrency, so even more people tried to buy GPUs at the same time. All these events caused a severe shortage. Customers encountered long waiting lists for GPUs or found that they were unavailable entirely. Scalpers sold GPUs at a substantial upcharge. Some people were unable to buy video games or computers they needed to complete work. The shortages affected heavy industry. Automobile manufacturers had to idle their factories, which impacted the factory workers' livelihoods and triggered a shortage in automobiles. This situation pitted knowledge workers, gamers, market speculators, and manufacturers against each other in a struggle for scarce resources. To what degree is this a problem? Do computing professionals have a responsibility to offer a technical solution, such as a technological alternative to GPUs? Do they have a responsibility to anticipate these kinds of unintended consequences? How should policymakers handle a shortage for a critical resource? Parallel programming. Parallel programming involves writing code that divides a program's task into parts, works in parallel on different processors, has the processors report back when they are done, and stops in an orderly fashion. C was not designed with parallel programming in mind, so we need to use third-party libraries for parallel programming in C. Some newer languages were designed with parallel programming facilities from the start. Parallel programming models and languages. A parallel programming model is a high-level conception of how the programmer can control processors and the data that moves between them. Shared memory. In the shared memory programming model, processes tasks share a common address space, which they read and write to asynchronously. Various mechanisms such as lock semaphores are used to control access to the shared memory, resolve contentions, and to prevent race conditions and deadlocks. One example is SHMEM, threads. This programming model is a type of shared memory programming. A thread is a single heavyweight process can have multiple lightweight, concurrent execution paths. A simple example of a thread includes a chat feature, video, or audio in an application like Microsoft Teams. Examples include pthreads, OpenMP, Microsoft Threads, Java and Python threads, and CUDA threads for GPUs. Message passing, a parallel programming approach where separate processes communicate only by sending messages, not sharing memory. Each set of tasks use their own local memory during computation. Multiple tasks can reside on the same physical machine and/or across an arbitrary number of machines. One example is the Message Passing Interface, MPI, that was first developed in the 1990s, hybrid model. A hybrid model combines more than one of the previously described programming models. Currently, a common example of a hybrid model is the combination of the MPI with the threads model. Other examples of hybrid models include MPI with CPU-GPU using CUDA, MPI with pthreads, and MPI with non-GPU. To program in parallel, you can extend compilers, translate sequential programs into parallel programs, extend languages, i.e., add parallel operations on top of sequential language, add a parallel language layer on top of sequential language, and define a totally new parallel language and compiler system. The extend language strategy, too, is the most popular, and MPI OpenMP are examples. Think it through. Multi-threading parallel programming. Why is it important at this time for application developers to turn to the multi-threading parallel programming paradigm and new emerging computing technologies for their application needs? Designing parallel programs. Designing and developing parallel programs has historically been a very manual process. The programmer is typically responsible for both identifying and actually implementing parallelism. Developing parallel code is often a time-consuming, complex, error-prone, and iterative process. For a number of years now, various tools have been available to assist the programmer with converting serial programs into parallel programs. The most common type of tool used to automatically parallelize a serial program is a parallelizing compiler or preprocessor. A parallelizing compiler generally works in two different ways, fully automatic or programmer-directed. In the fully automatic method, the compiler analyzes the source code and identifies opportunities for parallelism. The analysis includes identifying inhibitors to parallelism, and it may determine whether the parallelism would actually improve performance. Loops are the most frequent target for automatic parallelization. In the programmer-directed method, the programmer explicitly tells the compiler how to parallelize the code using compiler directives or possibly compiler flags. This approach may be used in conjunction with some degree of automatic parallelization. The most common compiler-generated parallelization is done using on-node shared memory and threads. If you are beginning with an existing serial code and have time or budget constraints, then automatic parallelization may be the answer. However, there are several important caveats that apply to automatic parallelization. Wrong results may be produced, performance may actually degrade, it can be much less flexible than manual parallelization, is limited to a subset, mostly loops of code, and it may actually not parallelize code if the compiler analysis suggests there are inhibitors or the code is too complex. The first step in developing parallel software is to 1. Understand the problem that you wish to solve in parallel. Next steps include 2. Partitioning, or breaking the problem into discrete chunks of work. 3. Identifying the need for communications between tasks. 4. Synchronizing the sequence of work and the tasks being performed. 5. Identifying data dependencies between program statements. 6. Performing load balancing to distributing approximately equal amounts of work among tasks so that all tasks are kept busy all of the time. 7. Establishing granularity as the qualitative measure of the ratio of computation to communication. 8. Managing I/O operations that are generally regarded as inhibitors to parallelism. 9. Debugging, a technique where the program is read through line by line to check for any bugs, parallel code. And 10. Analyzing and tuning parallel program performance. Figure 431 shows these steps. Flowchart displaying steps for developing parallel software. Figure 431 developing parallel software follows 10 important steps. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Link to learning. Parallel programming is a deep subject with many avenues for further study, from the low-level details of hardware and programming to high-level parallel algorithm design. Learn more about the introduction to parallel computing tutorial at Lawrence Livermore National Laboratory, using C with MPI and OpenMP parallel libraries. We focus here on how parallel programs can be written in the C language using an API, which is the most popular method. Some programming languages support parallel programming and may also be used to program parallel applications using message passing features that are built into the language itself. A message passing feature is a parallel programming approach where separate processes communicate only by sending messages, not sharing memory. The symmetric multiprocessor (SMP) model applies when programming multiple processors that are practically identical. OpenMP is a library for parallel programming in the SMP model. When programming with OpenMP, all threads share memory and data. OpenMP supports C, C++, and Fortran. The OpenMP functions are included in a header file called omp. An OpenMP program has sections that are sequential and sections that are parallel. In general, an OpenMP program starts with a sequential section in which it sets up the environment, initializes the variables, and so on. When run, an OpenMP program will use one thread in the sequential sections and several threads in the parallel sections. The parent thread is the thread that runs from the program beginning through end and starts and manages child threads. A child thread is started by the parent thread and only runs for a limited period in a parallel section. A section of code that is to be executed in parallel is marked by a special directive that will cause child threads to form. Each thread executes the parallel section of the code independently. When a thread finishes, it joins the parent. When all threads finish, the parent continues with code following the parallel section. Industry Spotlight. Artificial Neural Networks. The field of artificial intelligence makes heavy use of parallel computing. Artificial neural networks, ANNs, are a widely used technology that simulates the flow of impulses through nerve cells in a brain. An ANN needs to be trained by feeding it many examples of the kinds of inputs and outputs that it will deal with. This training process benefits greatly from parallel programming. A typical ANN has thousands of simulated cells and is trained on thousands of examples. This makes for millions or even billions of computations. Parallel computing is a great benefit because this training process can be performed in parallel. Hardware manufacturers, including NVIDIA, Intel, and Tesla, have even created GPU-based computers specifically for the task of training ANNs. Figure 4.32 illustrates the model of a neural network. Diagram of artificial neural networks. Input layer, hidden layers, output layer. Figure 4.32. The figure illustrates a fully connected set of layers in an ANN. In this case, computing the value maintained by each node requires combining values provided by all the node's input nodes, which explains why training ANNs requires so many computations if all nodes are fully connected to other nodes. Attribution, copyright Rice University, OpenStax under CC BY 4.0 license. Learning objectives. By the end of this section, you will be able to discuss the future of low-level programming, understand how the C language is used to develop firmware for embedded systems, develop kernel code using the C programming language. High-level languages are popular and have their place, but there are certain applications where only middle-level languages such as C will do. This section showcases two such applications, firmware and kernel development, the future of low-level programming. The economic trends that diminish interest in low-level programming are expected to continue and even accelerate. We are using wider varieties of computer hardware, not just personal computers, mobile devices, and servers, but also narrower segments such as tablets, set-top boxes, video streamers, and system-on-chip. So see computers such as the Raspberry Pi, Figure 4.33, photo of a Raspberry Pi 2 Model B, showing an HDMI port, audio-video port, micro USB power input, and two ribbon connectors. Figure 4.33, a Raspberry Pi demonstrates the concept of a system-on-chip, SoC. Credit, Raspberry Pi 2 Bear BR by Evan Amos /Wikipedia, public domain. The IoT is the growing network of products that are not used as a computer, but nevertheless contain an internet-connected computer. IoT devices include, but are not limited to smart voice assistant speakers, thermostats, home appliances, speakers, and tap payment systems. The computer embedded inside an IoT device is limited in terms of size, energy use, and cost, so it typically has a slow CPU and small memory. This makes middle-level languages well-suited to writing IoT software. Writing internet-connected applications in low-level languages is impractical, and high-level languages may not be efficient enough. Rust is a relatively new middle-level language created by the Mozilla Foundation in the 2010s. Many of C's positive features are also found in Rust. Efficient execution, portability, modularity, procedural and structured programming, and recursion. Rust has the capability to manipulate pointers, but adds native safety features so that the compiler can help the programmer prevent bugs related to pointers. The language also includes some features that are more common to high-level languages and are unavailable in C, including higher-level data types, lists, maps, and sets, macros, templates, and parallel programming. These features do make Rust more complicated than C, though. Since Rust has the same positive attributes as C, with some additional desirable features, we expect to see increasing use of Rust as a middle-level language. Global issues in technology. Naming of C procedures. It is a best practice to give procedures descriptive names that help a reader understand what the procedure does. English has been globally accepted as the language of programming, but this can cause some problems in non-English-speaking countries. For example, OpenFile is more descriptive than FOPEN. It is also difficult to tell what FOPEN might mean out of context, and especially if you are not a native English speaker. Unfortunately, procedure names in C are almost always written in English. How can this practice of using English names affect aspiring programmers whose first language is not English? How will it make it more difficult for programmers around the world to collaborate on source code? Firmware. Hardware is purely physical machinery, and software is purely digital code. To bridge this gap, we have firmware, which is very low-level code that communicates directly with hardware and provides a convenient interface for other software. Firm is the halfway point between hard and soft. If you want to learn to be an embedded systems engineer, it would be best to start from a simple hardware kit, rather than starting with the latest Intel or ARM chipset. Arduino is a hardware platform intended for creating simple, low-cost hardware for educational or hobbyist purposes. There are many series of Arduinos, but their Arduino PLC starter kit has a simple processor and comes with a guidebook. Atmega 328P has an 8-bit core, which is a good place to start digital circuit design and firmware development. You do not need to know how to draw schematics and layouts and assemble the chips. But you do need to know how to read schematics and understand how the chips are connected. Firmware developers should be able to read the schematics and figure out how to send data to the target device. Technology in everyday life. You and the Internet of Things. As IoT technology advances and computer parts get less expensive, more and more categories of IoT device are coming to market. Fitness monitors have helped people stay in shape. Smart thermostats have conserved energy and made homes more comfortable. Other types of home automation have improved quality of life for older adults and people living with disabilities. These technologies are enabled by middle-level languages that make efficient use of computer hardware, such as C. What is a new category of IoT device that does not exist yet, but would make your life or the life of your loved ones better? What kind of software would this device need? Could you write it in C? OS kernels and device drivers. The Raspberry Pi board has a Cortex-A53 processor that supports a 64-bit instruction set. This allows you to experience a modern processor architecture with RPi. Information relating to Raspberry Pi is constantly changing, and the best way to fully understand it is to tackle making your own kernel. There are several websites where you can do this. OS Dev Wiki. Older toy kernel that supports 64-bit long mode, paging, and very simple context switching. The Little Book about OS development. Operating systems. From 0 to 1. Making a toy kernel is a good way to understand modern computer architecture and hardware control. In fact, you already have a powerful processor and modern hardware devices on your laptop or desktop. This may be all you need to get started. The Qemu emulator https://www.qemu.org can emulate the latest ARM processors and Intel processors, so everything you need is already on hand. There are many toy kernels and documents you can refer to. You can install Qemu emulator and make a tiny kernel that just boots, turns on paging, and prints some messages. You do not need to make a complete operating system. Join the Linux community and participate in development. Link to learning. This step-by-step guide teaches how to create a simple operating system, OS, kernel from scratch. Each lesson is designed in such a way that it first explains how some kernel feature is implemented in the RPI OS, and then it tries to demonstrate how the same functionality works in the Linux kernel.